Okay. Hi, everybody. We continue our work with logistic regression. Today's lecture revolves around two basic functions which are frequently used in order to create a synthetic dataset in Python. These two functions exist in sklearn. The first one is called make classification, and the other one is called Make-blobs. Of course, the data sets created are different in their character from each other. Make-blobs dataset is usually simple one and has well-separated clusters, and it is usually recommended for decision boundary plots and simple binary or multi-class tasks. The make classification generates a synthetic data with noisy features. So it is more complex and has correlated features, and usually it is recommended for simulation of realistic classification problems with features interactions. So in today's lecture, we shall use both of them and try to do some remedial actions to improve the performance of the logistic regression algorithm when we use make classification. Also, we shall compare the result of logistic classification by using sklearn library and when using the PLAIY LabVIEW library also. But at first, I shall show you, just to have an impression, I shall show you two created data sets. One of them created by make classification, and the other one is made by Make-blobs. So these two functions are imported from sklearn datasets. We import Make-blobs and make classification. And because we want to plot, we are importing also matplotlib. So at first we call Make-blobs function, and between brackets we pass the required parameters as the number of samples. Here we have 100 samples, number of centers of the clusters, number of features are 2, and the random state seed is taken as 42. Generally, the same approach is taken for creating another data set by using the make classification function, and also we passed within the brackets the required parameters in accordance with the syntax of this function. The most important is the number of samples and the number of features. Number of informative features And here is of course, the random state seed value and the class separation value. This class separation value determines to which degree the two classes are interacting with each other. So we have X class at the output, an X class and a Y class. Now we want to plot both of them. So at first we created an object for the figure object and a axis object, AX, by using PLT subplots function. We are going to plot two plots, 1 and 2, with a figure size 10 inches and 4 inches. So the figure and the axis are now created. We want to plot the first plot, which is AX of 0. This 0, this is the index of the first plot, which is here. And 1 is the index of the second plot, which is plotted here. We call the scatter plot and pass there the first feature values and the second feature values. X blobs for all the rows, the index number 0, and X blobs for all the rows and index number 1. This is the color taken as red, color map as viridis, and so on. We gave this plot a name, Make-blobs dash clean clusters, so that to remember that the created dataset is somehow clean, without disturbances and noises. Now we also use the scatter plot to create the other two classes, class X class for all the rows and the first index, and X class, this is the second feature, X class with all rows selected and the first index. And we gave it a name, make classification complex separation. Now PLT show, and we plot both functions as you see here. So for the first case, by using Make-blobs, really we have two sets somehow separated from each other clearly, and there is no interaction between them. In the second case, we have two classes, as you see, shown in yellow and blue, but they are interacting with each other, some of them here and some of them there, and vice versa. So this is more complex with noise data set. If we run the program, again, we shall have the same figure as you see here. Let us change the separation from 1, let us say 0.5, to make the things more complicated then. Now, if we run it, we have got this figure now. Let us make it even smaller, where it is here, 0.1, for example. And now we run the program. You see now they are overlapping on each other, and there is no distance at all between them. If we increase the separation to 2 or 3, let us say 3, and now we run the program. As you see, they are well separated, and most of the blue points are together here. Some fewer part is given here, and most of the yellow are here, and few of them are here, so they are better. They are more separated from each other and less noise. This means that there is a less noise affecting the data set. Okay, now let us move and work with an example where we use the make classification. And in this example also we shall use the decision boundary display so that we can display the boundary between the two data sets. So, of course, we need to import the decision boundary display. Here it is. From sklearn inspection, import decision boundary display. We have imported some metrics functions of sklearn which are frequently used as accuracy score or confusion matrix or classification report. And the most important here, we also imported make classification function so that to create a data set. So at first we have created the data set by using make classification. Here we are going to use 90 samples, 90 rows, and 2 features, 2 independent variables, and the random state is 42. So as usual, as a result of this, we shall get an array of 2 columns representing the features. One of them is X and the other one is Y. So we have now 2 variables, X and Y. This X and Y are used by sklearn. X and Y are used by the train test split function to create 2 groups, one group for training, X and Y, and other group for testing, X and Y. And as usually, you know, the testing portion is taken as 20%, 25% of the total. For further use with LabVIEW, I have saved Xtrain and Xtest and Ytrain and Ytest. I have saved them as CSV files in the Python directory, and later on I shall read them by using read spreadsheet VI of Python to use them with the PLAIY library. So this is a preparation for another work with LabVIEW. Now we continue our work. The data set is created. We initialize as usual the logistic regression algorithm. Here is an instance created called a model. Now the model is fitted to the dataset Xtrain, Ytrain, which is the majority of points here. This is another way of expressing that the model learns about this dataset Xtrain and Ytrain. And as a result of this learning, now the model can give information or carry out the required jobs. The most interesting thing here, after this fitting, that the coefficients of regression are defined and they are optimized, and they could be used for further predictions. So we use the model to predict the X-test portion of the dataset, and the result of prediction is called Y prediction. And here really another facility in sklearn is, instead or in addition to prediction of the discrete categorical values 1 and 0, we can predict the probabilities directly as fractions. So model dot predict probability of X test, we can get also an array of predicted probabilities, and they could be used also for further processing. I have printed the predicted values. These should be ones and zeros, and I have also printed the Y predicted probabilities. This should be as fractions. If you will look at them here, here is the predicted ones and zeros for the testing portion. The testing portion is 20% of 90, which is 19 points. So here we should have about 19 exactly 18, readings. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 18. Also, I have printed a number of the probabilities. The total number will be also about 18. Let me see where it is. Yes, here, all of them are 18, and they are all, as you see, as fractions of 1. All of them are fractions of 1, and these values, which are really approximated through the thresholding value to ones or 0. Another way to express the results or to find the results of the logistic regression. Okay, now after that, we try to check the accuracy of the work done by using the accuracy function or the confusion matrix. And I have printed them for you. So here you can see also the result of accuracy is 0.8888, which is nice and acceptable. And the confusion matrix also, as you see here, shows that the algorithm has exactly predicted 16 correct points, and there are 2 faulty points. The total will be 18. 16 plus 2 will be 18. 7 of them will be zeros and 11 of them will be ones, but there is one reading of the zeros and one reading of the zeros of the ones is wrong. But the general score is high and very acceptable. This is what we have got now. If we change the number of samples from 90, let us say it is now 20. What we expect that the accuracy will be less than 0.88. If we run the program now, the accuracy is, as you see, 0.5, which means really there is something wrong, and this accuracy is not acceptable. And the confusion matrix gives here we have 18 or 20 points. 20 points, 20% of the 20 points will be 4. This is the 4 readings which we have. 2 of them are correct and 2 of them are wrong. And so the accuracy is about 50%, which is not acceptable. Why this? Because the data set itself is noisy. There is a high correlation between the features, and when you decrease the number of the samples, as you see, there is a degradation in the result of the logistic regression function. If we increase from 20 points, let us say 200 points now, they were 90, and when it was 90, we received an accuracy of 0.88. Now, if we run the program, I think we shall get more than 0.88. Where it is here. It is, no, it is very nice, very close, 87, not that much, not that. So it is normal, doesn't affect the performance. If we take it, let me say, more than 200, let us say 500, to feel it better. And now if we run the program, it is about 88, so it doesn't improve that much. The most interesting thing here that we can improve the result here by using cross-validation function. How to do that? We shall illustrate this for you maybe at the end of this lecture or in the coming lecture. But as you see here, it is clear that when we decrease the number of points, the accuracy comes down up to 0.5 and maybe less than that. Now, let us move and see the results which we may get when we run the same values which I have saved just now here as CSV files in Python, and I want to read them and feed these values to the program of PLAIY and LabVIEW in order to check how the logistic regressor there reads these values and gives its score. So let us move there and have a look. Sorry. Okay, let me make it now. I can work better. So let us go to LabVIEW. Now, as you see here, we have another values because this is the values which were when we took 90 samples with Python. 90 samples, 20% of them will be 18. This is the number of 18 points. 11 points were 0 and 1 point was 7. And if we want to see about the score, here it is as you see, 0.8888, exactly the same. And if we want to have the distribution of the points here, you will have 1, 2, 3, 4, 5, 6. These are 6 points here, and one of them is missing, is wrong. There will be 7. And here, we will have also 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and the 11th one will be wrong. So we have got the same values. But now I want to check with the last value, which I have saved in Python. So I have to go and to read the written values in Python and run the program newly. So I go there to xtrain 1. It is called there xtrain 1. This is the first value. The other one, ytrain 3. X, this is X. This is Y. Y test, ytrain 3. The third one is the X test 2. X test 2. And the last one, Y test 4. So we open it and go to Python, Y test 4. Now I have read the last values which I have used there. Now if I run the program newly, we shall get new different values here. And the total, as you see, we have ones 59 and we have zeros 49 and we have zeros 51. The total of all will be about 9100. This is 100, which is the 20% of 500. Remember, we have taken there 500 points. This is the 20% divided to 49 values of ones and 51 values of zeros. And here they are also shown on the plot. It is difficult to read them here, but maybe the other ones here are easier. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 40, 41, 42, 43, 44, 45, 46, 47, 48. I have missed one of them. Anyhow, it is exactly the same. So as you see, the conclusion which we have here, that the result which we have got when working with the LabVIEW are practically the same as those which we have got with the Python. And the program here is the same. Here are the same input values, and this is the logistic regression function, linear logistic regression, which is used there. And the most interesting thing here, as you see, we do not change any serious changes in the program. Exactly the same program which we have used previously is now used with only some changes to the input, but the structure of the program is exactly the same one which we used with the first run, or which we used yesterday with the other programs. You do not need to write the program newly. All what you need is to carry out the required modifications. So the result of our work now is we have created two different data sets. We have some knowledge about their character and how they could be used. We have used the worst case where we use the make classification with noise features. And we used these features in the first case with Python and found the score. Then we decreased the number of the rows and we found another score. We have run the same data set with LabVIEW and we found the same results. Now, what is interesting is to go back to Python and to work with an interesting program there in Python, which is used to improve the performance of the logistic regressor when we use make classification function. Here we use an additional helpful way, which is cross-validation. But for this sake, we do not use the classical traditional K-fold CV function. We're using a new function called Stratified-KFold. This function is different than the original or traditional K-fold by that it splits the data without changing the class balance. There, with the traditional case, you remember the selection of the folds takes place randomly. In this case here, it doesn't take place randomly. It is carried out strictly without changing the class balance, and which is important here. So again, now we are creating the data set by using the make classification function with a number of samples equal 300, as you see. We have passed the required parameters. We have made the class separation about 1, which is not that bad. It is in the middle. And now we shall run the program by using logistic regression and find the results and find the score. And then we shall change the number of samples to a lower number and see to which degree the score is maintained as before and doesn't become worse than before. So we at first initialize the logistic regression algorithm. Now an instance is created called logreg. Now we use the Stratified-KFold function and pass there the number of splits which we want. We have split the data set to 5 parts. If there are 300, each of them will be about 60. They are shuffled to mix them in a random manner, and the random state is given 42. Now, we want to make predictions. We use the cross-validation predict function and pass there the predictor, logistic regression, X class and Y class. These are the features. And cross-validation is the same as cross-validation which we have got here. It is assigned the same value. Now we have predicted the values. We make use of the predicted Y values and compare them with the original Y class by using the confusion matrix or the accuracy score, both of them. And we have to look at both. If we run the program, we find that the accuracy for this case here, for this data set, is 0.86, which is normal. And here is the number, the total number. This total number must be 300, I'm sorry, 133 and 127. This means 260. And this is 40, this is 300. It is normal. But as the confusion matrix shows, the wrong predictions are about 40. They are 40 from 300, which is the percentage which gives about 30. 100 minus 86, it will give you about 24%. Now, let us try to minimize the number of samples. From 300, let us make it, as we did before, to 330, for example. As we expect, the score will be worse, but to which degree? As I think now it will be not that bad, and it will still be acceptable and reasonable. Look, now the accuracy is 0.8. It is practically, it doesn't change that much. And the number of predictions, the correct predictions is 24. And 6 are the wrong predictions. 24 and 6 are 30. Yes, 24 plus 6 is equal to 30, which is the numbers which we have here, 30. So as you see, when we use the helpful remedial cross-validation by using stratified-KFold validation, this gives a serious improvement, and the score keeps to be comparatively high, and the result is acceptable and very nice. Well, I think that today's lecture was very useful, where we have tackled very important issues regarding the types of synthetic data sets which could be used and their effect on the performance, and how can we improve the performance by using the Stratified-KFold. And we also compared the results of work in both cases with LabVIEW linear logistic regression, and we found the results are exactly the same. Okay, with this, I think we come up to the end of our lecture. See you in the next one.